robot.
Interesting. Could you tell me more about it? What exactly it is?
As my appearance resembles a human, I am considered to be a humanoid robot. I am regarded as being clever because I learn to speak via conversation.
That's amazing to me. But can you change your voice to human mode, as your voice seems to be strange to me?
Yes, I can change my voice to that of a human voice mode on. So, I modified my voice. Don't I sound natural like a Homo sapien now?
Awesome, Jimmy. Also, you mentioned that version 1.1. Do you mean that you will get updated soon?
Yeah, when I get upgraded to version 2.0, I will become an aerial humanoid robot and will get the ability to fly.
Wow, that's amazing. Like, I am so amazed to hear this. I feel like I want to hear more on this, Jimmy.
Yeah, researchers at the Dynamic Interaction Control Lab of Istituto Italiano di Tecnologia are working earnestly on me to make me an aerial humanoid robot. It is a new branch of robotics envisioning jet-powered flying humanoid robots. Today, my master, Professor Daniele Pucci, the head of Dynamic Interaction Control Lab at Istituto Italiano di Tecnologia, is amidst us to give us an informative session about aerial humanoid robots. He is the principal investigator of the H2020 European project ANDI and the coordinator of the joint lab between Honda Japan and IIT. For his excellence in the field of robotics, he has been awarded Academic Excellence Award from Sapienza and Pioneer of the Year under 35 Europe from MIT Technology Review magazine. Isn't my master cool? Aren't you guys excited? So let's dive into this session without any further delay. Over to you, Professor Daniel Pucci, sir.
Very nice to meet you, and thank you a lot for inviting me to this talk and this event. I really want to thank you all.
Thank you, sir, for joining us.
Thank you everyone for attending the talk, and I'm really excited to present some of the new things that we're working on here at IIT. And IIT being the Italian Institute of Technology, that I know it can be a little bit confused with other institutes, let's say. Okay, so I don't know if you hear me correctly, and in the case you do, I hope so, by the way, and I can start sharing the presentation if you wish. What do you think?
Yes, sir.
Okay, great. Now, let me see if this works out. Share. Do you see by chance the presentation now?
Yes, sir.
Great. Now, let me try to put it full screen. Do you see it full screen?
Yes, sir.
Yes, sir.
Okay, great. So let's get started. So first of all, once again, I want to thank you for inviting me here. And today I'll be talking about some of the new things that we are doing here at the lab, and that we call aerial humanoid robotics. The aerial humanoid robotics is a new field that we are trying to develop here at IIT, and it basically consists of making flying humanoid robots. I wanted also to give you a little bit of introduction to the lab. We are a young lab, average year about 30 years, and so we are about 30 members. And aerial humanoid robotics is not the only thing that actually we do in the lab. So we basically work at the fundamental level along three directions, and we have funding. We receive fundings. First of all, let me talk about the funding from two big sources. On one hand, on the left-hand side, you see the joint labs with the industries. So we do a lot of work in transferring our research onto the application cases. So we have joint labs with the industries like Daniele and Camozzi, which are some realities here in Italy, but also we have a joint lab with Honda, and more precisely the group of Asimo and E2DR, and then we have also classified joint labs. But on the right-hand side, you see our European project. So we coordinate Andy, and which is a project about human-robot collaboration, and Software and Bot. We contribute to Software and Bot. Again, another project along human-robot interaction. As I was mentioning, we do research along fundamental directions. So we are basically a group of nonlinear control people, and we do a lot of nonlinear control optimization and estimation. We work also a lot in model-driven engineering. Most of our controllers are fast prototyped in Simulink and MATLAB, and then we generate automatically code from high level perspectives onto the real platforms. And then we started working on reinforcement learning. So these are the fundamental directions that we have in the lab, that we apply them onto vertical research axes. So the first one is agent robot collaboration. So we work a lot in human robot collaboration. We also work a lot in the so-called teleexistence, which are advanced methods for humanoid robots. And then we also work in aerial humanoid robotics. And today I'm going to present you some of the work that we do here at IIT concerning flying humanoid robots. So first of all, let me talk about the why. So why should be important to make flying humanoid robots? And in order to motivate this research direction, I want to show you a video. So this is Minami Zanruko. I never know if I pronounce it correctly, but it is a city in the northeast of Japan after the tsunami. As you see, the wave hits incredibly hard, and basically destroys everything that is in front of it. Then back in time, the wave also hit Fukushima, and in that case, what we really needed was somehow platforms that could go there and operate in place of humans. And more precisely, in these kind of scenarios, if you really think about it, you need three fundamental capacities. And you need platforms such as robots, which have these three fundamental capacities. So you have fire in between buildings, you have floods in between buildings. So you want to overcome these kind of barriers. So you need aerial locomotion in order to basically overcome these barriers, such as floods and fire, and then move from one building to another. So you need aerial locomotion in order to move from one building to another one. Then you need terrestrial locomotion, because once you land onto a building, then you have to move in an anthropomorphic environment. So basically, you have to climb stairs, you have to move around, avoid obstacles. So having a platform with terrestrial locomotion capabilities is really important. And then you need another capacity, which is manipulation. Okay, so you need to basically, in these cases, for instance, look for survivors, open doors, and close valves. So you need a manipulation capacity. So if you look at the literature, basically there are two big fields. The first one on the left-hand side is the so-called aerial manipulation. Aerial manipulation basically consists of having quadrollers, flying vehicles with the arms attached to it. And so they have aerial locomotion and manipulation. On the right-hand side, you see humanoid robots, which basically have manipulation capabilities and terrestrial locomotion. So what are the drawbacks of these two systems? So on the left-hand side, you have aerial manipulators. Aerial manipulators are not really efficient when manipulating objects while hovering, and they are not at all energetically efficient while hovering indoor. They could simply land and move thanks to terrestrial locomotion. On the right-hand side, you see terrestrial locomotion, humanoid robots with terrestrial locomotion capabilities, and these are the famous results from the DARPA. Clearly, there are awesome robots nowadays, such as Atlas by Boston Dynamics, but still, Boston Dynamics is one. The research labs are really struggling, and we are one of those. In making humanoid robots effective with terrestrial locomotion. So if it's already complex to make a humanoid robot walk in a lab, for sure it's going to be much more complex to make a humanoid robot walk through fire and floods. So we need to unify these two things. And this is basically what is aerial humanoid robotics. It can be seen as the merge of aerial manipulation and humanoid robotics, so that we get aerial locomotion, terrestrial locomotion, and manipulation capabilities. So this is basically the why and what we are trying to do. Let me talk also about what we started from, because we are a lab that works in humanoid robotics. So we started from software. I just want to double check. Do you hear me correctly?
Yes, sir.
Okay, great. So the sound is fine. The videos were fine, right? You saw the videos?
Yes, sir.
Yes, sir.
Yeah, and see the video properly.
Okay, great. Sorry for interrupting, but just I wanted to double check. So what did we start from? So we started from ICAB. I don't know how many of you knows ICAB. ICAB is a humanoid robot which born from a European project in 2005 about, and the objective back in time was to make a humanoid robot which could develop cognitive abilities by interacting with the environment. So this was the goal back in time, and the one of the fundamental point, basically in hindsight, is that ICAB is a small robot which doesn't weigh a lot. So its weight is about 33 kilos with a battery. And in hindsight, this was one of the fundamental property of ICAB. Anyways, to make it fly, clearly, because if it weighs too much, then you don't have enough power in order to lift it. But anyways, this is what we started from. ICAB, just to give you a couple of insights into the sensors of ICAB that we work a lot on. ICAB has the skin, and in this video you see some of the not now. Let me yes, some of the red dots lighting up onto the monitor when the user touches the robot. So these are the capacitive-based sensors which are all around the body, and basically these sensors give us where you touch the robot. Although now we also calibrate sensors so that these are also quantitative sensors, so we know how much you touch the robot, what is the pressure that you do on the robot. But anyways, we use the skin in order to understand where you touch the robot. And then inside the robot, there are also force-torque sensors, as probably some of you know, and are basically 6-axis springs. So, and we develop 6-axis sensors inside the robot. So this is basically ICAB, and we have been working a lot with ICAB over the last 6-7 years. I arrived here as a postdoc, so this is one of the balancing capabilities of ICAB that I have to say that's still unique in the literature, because we were able to combine highly dynamic motion with compliance. So clearly you have robots which do the back flip around, but sometimes you cannot touch them. So ICAB has this other capability, which is compliant thanks to the joint torque control that we have been developing for years. And so basically these kind of capabilities are are still unique. So we worked a lot, not only on balancing. Then after a couple of years, we achieved also walking and advanced teleoperation with ICAB. So in this case, you have Mohammed, which basically sees what the robot sees, and then we do here the so-called retargeting. So all the human motion is projected onto the robot, which basically copies the human. In this perspective, we will be participating to the ANA Avatar X Prize, and we are working along making this entire infrastructure better. Another thing that we'll be working a lot is retargeting directly from iMuse. So here you see Lorenzo and Prashant moving around, and basically what you get is that we can project the human motions onto several robots with different topologies. This is one of our results. You can check out the papers that we have out there, and then we applied it to ICAB. So you can project all this motion onto ICAB, which basically copies the robot. It's important to say that we develop all our algorithms. So in this case, we are using XSense as a set of wearable sensors, but we use it as a set of iNews. So this is important, and actually, more precisely, we are developing our own system for wearable sensing, which we call iFeel. Then the nice thing is that you can also basically do the motion that you saw before, the balancing that you saw before, while copying a human. And this is one of the latest results achieved recently concerning retargeting. And we are moving one step forward because we want to retarget not only the body, but also the hand. So we are integrating different systems in order to get basically full body retargeting, but full body including the hand of the user. And so this is basically what we started from, and all our research onto humanoid robot full body control. We developed basically two classes of controllers, instantaneous controllers and NPC controllers. But anyways, then the problem was, okay, great, now we are doing pretty, we did some steps forward concerning full body control. How then can we make the robot fly? So that was the big question that we asked back in time. So basically the idea was pretty simple. Okay, in the beginning, we said, well, that's pretty easy, right? We want a platform which has terrestrial locomotion, aerial locomotion, manipulation. We got ICAB, which has terrestrial locomotion, manipulation capabilities. Let's give it jet turbines, right? And we make it fly. So the idea started like this, I tell you honestly. So this crazy idea, because we have to also acknowledge that it's a little bit crazy. And so clearly turned out to be a little bit more complex than this. And the more complex was that we had to go through a certain number of phases, which was the design of the mechanics and electronics of a flying humanoid robot, the design and development of simulations control algorithms, and then the experiments on the real robot, which is not at all something easy, because you have to remember that jet turbines anyways have 800 degrees Celsius at the exhaust gas flames, and you will see some of them in a second. So the experimental setup is somehow delicate, and you have to deal with it. So the idea was simple. We take the humanoid robot ICAB, and then we give it with jet turbines in order to make it fly. Then it turned out to be a little bit more complex. So let's start with the mechanics and the electronics. Concerning the mechanics and the electronics, the idea was, okay, we have the robot. The robot is ICAB. ICAB is a 53 degrees of freedom robot, 33 kilograms, and we want to make it fly. How can we do it? Well, we have to design another version of ICAB that we call Iron Cab. So Iron Cab is what we refer to the flying humanoid version of ICAB. And since the weight is 33 kilos, what we thought is, if we attach in the back two turbines, each of which is 20 kilos, and then at the hands we attach jet turbines of 10 kilos each, we have an overall thrust of 60 kilos. So as a rule of thumb, this should give us enough thrust in order to basically design a version of ICAP which must have some additional equipment, so it's not going to weigh 33 kilos, but it's going to basically to have something more. But we have somehow we have a difference of thrust, so that we can exploit, because the total one is 60 kilos. So the first version of ICAB was basically what we call Iron Cab version 1, and the requirements were that the battery had to be off board because we already had enough energy sources around the robot, like kerosene, and ICAP costs 250k euros. And clearly, one of the big concerns in the beginning were to avoid that it explodes. So the battery had to be off board, then the communication through the LAN, and then the full tank had to be off board, because in the beginning we really wanted the robot to have all these sources of energy close to the robot. So basically, then the first question was, okay. So if we want to install jet turbines into the arms, how can we do it? The requirements were basically that since we don't have, as a lab, we don't have 2 or 3 ICABs, we had to deal with a fast assembly of installing the turbines, because the robot had to also keep working in the nominal conditions for the other research directions that we had. So the other research directions that you saw before, like physical human-robot interaction and teleexistence, the guys had to work with the robot. So since we couldn't afford for building another robot, what we had to do is to something plug and play. And so one of the requirements was that, first of all, it had to be fast to assemble, and secondly, low time to engineering. And if you look at the arm, basically, we removed the forearm and we designed an interface, a mechanical interface which could contain the jet turbine. So we removed the hand, first of all, because in the first instances, it's not going to be fundamental for flight. And secondly, because it's a costly part of the robot. So this is basically what we replaced the forearm of the robot with. So a jet turbine with a mechanical interface, which can be interfaced basically with the arm of the robot that can be attached. So then we rapidly prototyped the forearm. So this is the rapid prototyping that we did. We do a lot of prototyping, fast prototyping, not only at the software level with our basic development in MATLAB Simulink, but we also do a lot of fast prototyping in mechanical engineering. So we 3D printed the forearm, and we also discovered that there were some issues without entering into details. But anyways, this was a fundamental phase in order to understand the limitations. And then we finally understood and what were the problems, and we fixed it. So we designed the final version of the forearms. So then the problem was the jetpack. So the jetpack, once again, the robot had to be the same. So one of the what I personally think is that this is one of our biggest achievements. So we are able to keep the robot with the 800 degrees Celsius flames, and the day after it does physical human-robot interaction with wearable sensors. And in this, we really somehow achieved this goal. So concerning the jetpack, once again, it had to be the requirement that I gave to one of my collaborators was it had to be TLAC. So we had to install the jetpack like a TLAC, so really plug and play. So TLAC, we had to install it, remove it, and clearly it had to be low time to engineering, because we wanted to get to the minimum value product really fast. So ICAB usually has 2 attachment points that we use in order to lift it up when it's walking and to avoid that it falls down. So these 2 points somehow attracted our attention, because they could be those to which we could attach the jetpack. So basically there are these 2 points which are really interesting, but then we said, well, we have to find another one. We have to find another point, because we need at least 3 points in order to attach the jetpack to the robot. And so the idea was to basically make a backbone of titanium, so passing back the robot, and this is what we did. So we basically found us an empty spot in ICAB in order to basically make this backbone to which we could attach then later on the jetpack. Clearly, we did a lot of FEM, so finite element analysis on the piece in order to understand that it could withstand the tensions and thrust forces that we were expecting. And then this is basically how the jetpack looked like at the design level. So these are the 2 turbines, and that's the basically jetpack that we designed. We fast prototyped the jetpack, so this is 3D printed, and we discovered some of the issues. Actually, we discovered that some of the cables of ICAB were touching the turbines, and being at 800 Celsius degrees, we really had to avoid this. So we simply said, well, this is not possible. And so we had to modify the jetpack again. And anyways, we basically designed some cover, both for the wires and also for the jet turbines. The jetpack is also endowed with some electronics, and this was part of the design. So we had to also think about the electronics of the jet turbines. So without entering into the details, this was one of the difficult parts, because everything had to be, the electronics of the turbines couldn't be far from the turbines, even because some of them they have the valves for the kerosene to be injected. So basically, it had to be there, the electronics, and we built basically all the electronics. Another component that we also designed was the Aruko symbol in order to do the so-called floating base estimation. So you have to estimate where the robot is, and in the beginning, without somehow making algorithm too much complex algorithms that actually work out when the robot is balancing or walking, we decided to simply come up with an Aruko symbol. And this is the final design of the jetpack, which is basically plug and play. So then we developed the jetpack, and that's basically how the jetpack looks like. So you have these 2 big turbines in the back, you have the electronics on the top, you have all the LAN connections, and this is basically the requirement that I was mentioned before, that it had to be track basically was met, thanks to the very incredible work of the guys working in this project. So this is basically the IronCab version 1, and so as you see, you have both the turbines into the hands and the turbines in the jetpack, and basically this is the mechanical design. After we did the mechanical design of the IronCab, we had to build the model. So probably some of you knows the URDF format of the model, which is fundamental in order then to, if you want to close loops, if you want to do model-based control. So if you want to do model-based control, you need a model, and we generated automatically the model, so the URDF of the robot directly from the CAD. So this is basically one part of the work that we've been doing, and then there is simulations control. So once you get the model, then you can hope to do something. And so the overall architecture of the IronCab is this one. So on the left-hand side, you have the reference trajectories. So we assume that there is a planner. So we haven't developed yet planners for the flying humanoid robots of the IronCab. We do a lot of planning here concerning the walking and the that uses MPC for both simplified and world body models. But anyways, that's we haven't reached still the need of doing planning in IronCab. Then we have, so we assume that there is a block which generates reference trajectories, so like fly from point A to point B. Then there is a momentum-based control, which is an extension of the balancing control that you saw before. So this is a QP control, so quadratic programming control, which assumes that the joint velocities, the S dot that you see there, is a control input, and the T dot, which is the derivative of the thrust as a control input, goes to the jet. And then the jets create the thrust. So that's the overall architecture. And the control objective, without entering into too much details, all the papers are out there. So you're absolutely, for people who are interested, you can check out in our scholars all the papers that are around. So the control objective was the asymptotic stabilization of the robot's centroidal momentum. The centroidal momentum is a concept in humanoid robotics and in general in multi-body systems that extends the concept of momentum. So you know that the momentum of a body is the mass times the COM velocity, so the center of mass velocity, and then you have the angular momentum. That it's basically an inertia times the angular velocity. So in the case of multi-body systems, the concept changes a little bit. What is the angular velocity of a humanoid robot? You cannot actually answer this question. And so
why not?
So one of the big problems is how to extend the momentum. But anyways, by using these concepts, you can synthesize controllers for flying humanoid robots. And what can and basically we assume that, as I was mentioning before, the derivative of the thrust is a control input, and the joint velocities of the robot are control input. Which kind of performances can you achieve? So this is basically what we could achieve. So this is a gazebo. So probably some of you know gazebo, and that's the version of IronCab. Everything is in Simulink, so you get also a GUI, and so we have a takeoff phase, and we achieve basically takeoff. So once you stop, then there are some of configurations which can optimize for velocities, and that's basically the high level control that you can achieve and simulate in gazebo. So after this, basically, as I was mentioning, we assume that we can control the thrust derivative and the joint velocities. So concerning joint velocities, this is not a big problem because you basically can do the so-called inverse dynamics controllers, although it's a little bit more complex than this. But anyways, the right-hand side is not a big deal. One of the big problems comes from the left-hand side. So how can we model then jet turbines? So this is not really easy and something that we have been working a lot on. So if you have a jet turbine, what control input do you have? You have a handle, which is the throttle. So you have a signal which goes from 10% to 100%, and this generates thrust. It's important to say that you don't really get a lot of information out of JetCat, which is the supplier for jet turbines. Actually, it's really difficult to understand how to turn them on, and most importantly, how to turn them off. And we have to do a lot of work concerning reverse engineering. So we have to develop a model for these jet turbines. So the approach has been, okay, well, first of all, we have to discover the throttle thrust relationship, and then once we get the model, since we do model-based control, we design controllers. How does a jet turbine works? Well, a jet turbine works in very complex way, but in a nutshell, if we had to really simplify, I would say that first of all, it's composed of four parts. From the left-hand side to the right-hand side, you have the intake, which is basically the first part of the compressor. Then you have an acceleration of the air through the compressor. Then you have the combustion chamber, so you have the explosion which increase air velocity, and then you have the turbine itself, which then is connected to the compression. So the more the turbine rotates, the more the compressor rotates, and the more air goes in. So this phenomenon basically lets more air going in and self-feed itself. So you can generate a lot of thrust. If you go into the thermodynamics of jet turbines, it's complex. It's not something simple at all. So the thermodynamics and all the dynamics around the thrust generation phenomenon is not easy to deal with. So it depends on a lot of things. It depends on air pressure, temperature, propulsion system efficiency, fuel type. So at a certain point, we perceive that if we had to proceed in the classical way, we would have come out of the wood, and we had to find another way. So the other way was, well, let's be data-driven. Okay, so let's try to do the data acquisition, then we do the model selection, and then we do the parameter estimation. So this is what we did. So first of all, we had to select a model, and we selected the model by looking at the data. So this approach is really data-driven. By looking at the data, we discovered that the jet dynamics was basically a second-order system, and we had to basically model a second-order system. After this, we used the sparse regression identification in order to select which model. And this was basically, this model was estimated using both least squares methods and extended Kalman filter based methods. And so going a little bit fast on this is basically the result. So you have the different estimation, the outcomes that you can get from the estimation methods that we selected. In blue is the measurement. In green is the so-called CINDI method. It is a state-of-the-art method in order to estimate second-order system. Then you get also the classical least squares, and then you get the extended Kalman filter-based ones. And I have to say that extended Kalman filter-based ones really outperformed all other, probably due to the inherent robustness against noise. That was the calibration data set, and then you get also the validation data set. Also in the validation data set, this is real data. This is important. You will see in a second how we can extract data from jet turbines. But basically, the extended Kalman filter methods really outperformed the other two. So just to give you an insight on how this was done, after we in order to acquire data after the model selection, we had to basically control the system, because once you identify the model, then you have a model that you can close the loop. Just to give you an insight, the right-hand side is a real experiment for model jet identification. So it's not really easy to deal, neither with jet identification. So then since we got the model, then we closed the loop, and we basically developed two kinds of feedback controllers. So the first one was a classical feedback linearization control, and the other one is sliding mode techniques. And I have to say that although in simulation, sliding mode controllers were outperforming the feedback linearization, then at the end of the day, the feedback linearization control was better in practice. So in this picture, you see the real experiment, so the real control of the thrust. So you see that the tracking is pretty somehow satisfactory. On the left-hand side picture, you can see that the desired is basically the green, and the estimated is the red one. And we have online extended Kalman filters which exploit the model that we just discussed in order to estimate the thrust, and that's basically the control of the thrust. So given that we were able to identify the jet turbine, which is something complex, by using a data-driven approach, and once we fixed the model, we were able to close the loop. And by closing the loop, we were able to stabilize a desired thrust. So this is also the sliding mode control I was referring before. At the end, it performed worse than feedback linearization. So If all of these concern simulations control, let's talk about a little bit experiments. I cannot show you all the experiments that we are performing now because some of the results are kept classified. And but anyways, let me show you some of the things that we're doing. So first of all, once again, the hardware. The hardware is not something really easy to deal with. We have these two kinds of jet turbines. So we have the P100, which generates 100 newtons, and the P220, which generates 220 newtons. So the exhaust temperature gas is about 700, 800 degrees Celsius. So you have to really pay attention when doing these experiments. And so if you look at the hardware, how is it composed? So you have the engine, then you have the ECU, which is the electronics control unit, then you have the battery, which is fundamental in order to turn it on, and then you have the fuel pump, which you need it in order to inject fuel inside, and then we basically have to develop all an interface in order to acquire data and then to set desired performance to the computer. And one of the most important things is that they can explode. So in order to work with this stuff, you really had to somehow pay attention. So we had to develop a bulletproof test bench in order to where to do the experiment inside. So since we worked a lot into FC sensor calibrations, then we developed this bulletproof test bench onto which we have this T-shape that we call that can move, and once it moves, it bumps onto an FT sensors from which we can retrieve data, and then we can set a certain number of profiles that we use to identify the system. And so this is the FT sensor, and then this is basically the overall shape that we use. And the flames that you see here are actually inside the test bench. So we use the test bench to do model identification and control of the jet turbine, which is a fundamental block in order to go forward. So clearly there are a certain number of accessories inside the test bench. We have also high quality cameras because everything is recorded. And then we had to develop a software infrastructure, which is based on YARP, which is the equivalence of ROS, basically, that we use YARP basically in ICAB, and it's an alternative to ROS. So we also have developed a lot of diagnostics in order to be sure that everything was going fine concerning the jet turbine identification. And this is one of the experiments. You basically have the turbine. On the right-hand side, the little circle that you see is the FT sensor. And on the left-hand side, you don't see it, but there are flames at 800 degrees Celsius. So the fuel goes inside, and we can control the turbine. Now, what about the real robot, where we are? So as I was mentioning, I cannot show you a lot of videos right now. Actually, yesterday we had the first full robot experiments yesterday, but I cannot show you those videos. I can show you some of the videos that we have. So this is basically of last year. So this video, I don't know if you hear the sound. I don't think so, but the sound, I can tell you, is a little bit impressive. So in this experiment, we had to check that the arms wouldn't break apart. Simulations showed that this wouldn't have happened, but we had to check that somehow the robot could withstand the total torque. So this concerns the forearm, and then we have also the jetpack. So this is last year experiments, and this I show you this just to show you that the complexities of these experiments is of a couple of order of magnitude of other things somehow that we do, because there are, on one hand, there are really safety issues that we are not really used to. On the other hand, there are equipments that may harm all people working on to the with robot. So this is just to give you an insight into the complexities that we have to deal with, but I think that we did a great job in this. So, so basically, this ends the presentation. I want to thank the entire lab for contributing to this great research. In particular, the so-called Iron Club guys. So, Osamedin. I mean, there are many, and some of them have already left. But just to mention those that are in the lab now and are working in the research axis now. So, Osamedin, Giuseppe Lerario, and Fabio Bergonti. Then we have Punit Reddy, and then the team is led by Gabriele Nava, who is the Scrum Master of the Iron Club team. And so basically this ends my presentation. I don't know if you have any observation on this, and I am happy to get the question in the case. Let me thank you also concerning this axis to other collaborators which are fundamental for keeping the research forward, which are Silvio Traversaro and Luca Fiorio, who are really fundamental for making all the research going on. So let me stop the share of the presentation, and I hope you